Simple harmonic motion. The amplitude of an oscillation is the maximum positive displacement from equilibrium. An object oscillating under the influence of a Hooke's law restoring force, F equals negative kx, is called simple harmonic motion. The angular frequency omega equals 2 pi over t, the period t, and frequency 1 over t in simple harmonic motion are unaffected by changes in the oscillation amplitude. This includes damping forces. So damping forces will have no effect on your angular frequency period or frequency. Simple harmonic motion is identical to the projection onto the x-axis of the motion of an object in uniform circular motion. So if an object is going in uniform circular motion and you were to plot one point of uniform circular motion on a position versus time graph, it's going to be an identical graph to an object in simple harmonic motion. For simple harmonic motion to be occurring, you have to have that restoring force pointing back to the equilibrium. Also, your restoring force or your acceleration is proportional to your displacement. As you get farther away from your equilibrium point, your displacement is increasing, so your restoring force and your net acceleration are also increasing. Graphs of position, velocity, and acceleration in simple harmonic motion are sinusoidal curves. In each of these graphs, the phase angle shifts the location of the vertical axis, which is just where time equals 0, either to the right or to the left. Remember, sine starts at 0 and goes positive, cosine starts positive and goes to 0, negative sine starts at 0 and goes negative, and negative cosine starts negative and goes towards 0. An example of position versus time graph, sinusoidal curve, is here. This is not a sine graph, though, because notice it starts positive and then goes to 0. So this is a cosine graph. So the function in the equation would be cosine. A shortcut for you to determine the acceleration versus time when only given position versus time, rather than taking the derivative twice, you can just recognize that acceleration versus time for this object in simple harmonic motion is just the mirror image of your position versus time graph, flipped along the x-axis.